Hello everyone, my name is Aiden Hughes,
And I'm Ethan Onspach.
and this is the carbon fiber filament winder project. And just to give everybody a brief introduction on what a composite is, it's actually a material that composes of two different constituents. The first being a structural fiber, such as a glass filament, or in our case, a carbon fiber filament. The second is a polymer that adds a little bit more structure and rigidity to the filament, and this can be an epoxy or a resin.
These materials are most often used in industries where high strength and low weight are critical, such as the aerospace industry, where the fuselage of most aircraft are made out of composite materials, an example of this being the Boeing 787. Filament winding is a process used to create any composites with a continuous exterior profile, such as the airfoils of aircraft or composite tubes or pressure vessels. On the filament winding machine that we designed and created, the fiber starts on a creel. It is then pulled off the creel and through a resin bath containing the resin. The fiber then passes through nip rollers that remove excess resin. After this, the coated fiber is then wrapped onto a rotating profile called a mandrel. While the mandrel is rotating, the resin bath platform actuates left and right so that a specified tube length is created. This continues until a desired tube thickness is reached.
Once this winding process is completed, the mandrel is removed from the winding mechanism and is placed into an autoclave where the sample is exposed to high temperatures and pressure. This is a very energy inefficient and time-consuming process, which takes multiple hours or even days for the resin to fully cure. And a great example of this is here at CSU, we manufacture a small 4" by 4" composite panel that has a curing cycle of 5 hours. And this is pretty standard for objects in industry. But ultimately, for our project, we seek to remove the secondary heating process from filament winding.
So to remove the secondary curing stage, a novel formulation of DCPD resin was used as the binding polymer. This resin quickly undergoes an exothermic reaction that cures the composite fully once the part begins to reach a temperature of approximately 70 degrees C. In order to cure the wound part, we explored two different heating methods. The first of which is a resistive heater that's simply inserted directly inside the mandrel to heat the whole surface. This produced parts very quickly, however it had some issues. The second is an infrared heater, which is placed above the mandrel, providing radiative heat transfer. This cured slightly more slowly than the resistive heater, however the mandrel could continue rotating, mitigating some of the issues that Aiden will speak about.
And actually, in this current setup that we have here, we were able to fully wind and cure samples in as little as 12 minutes. This was actually done with the resistive heater, and the samples that can be seen on the left, so your right. And the biggest issue that we saw here is when we started to cure, the resin had time to actually accumulate on the bottom of the sample before fully curing, allowing for an uneven distribution of the resin. This was contrasted against the IR heater, which took 3 minutes more to fully fully cure. And these were seen on the right. It had a lot more even resin distribution, allowing just for a better overall sample. And we were able to also contrast these two different heating methods and found that the IR heater would be better suited for implementation into industry, as it is fully independent from the mandrel diameter, and it can be easily integrated into a lot of current winding mechanisms. It also allowed for significantly higher quality samples.
Ultimately, this project demonstrated the feasibility of using the self-curing formulation of DCPD in the filament winding process. We were able to manufacture carbon fiber composite tubes considerably faster than the current industry methods. Additionally, we demonstrated the feasibility of both resistive heat and infrared radiation curing methods in this process. In conclusion, the IR heating method was the most feasible curing method we explored due to the consistency of resin distribution and the ease in which IR heat sources could be potentially installed in any existing filament winders in industry.